So good day, everyone. My name is Christian. Thus, a happy Easter to all of you. I'm so delighted to introduce to you a real special person, because a very young special person, Andrealuna Pizzetti, which is a beautiful name. From Italy, she's now at Clemson University, a Ph.D. candidate in South Carolina. And what's amazing, she's also an iTelescope enthusiast, so she has had an account for quite some time. So Andrealuna, please join us. The name Luna already tells you everything, right? So she is associated with the moon. Andrealuna, so nice to have you here. How are you?
Hi, Christian. Hello, everyone. Thank you for having me here. Yeah, as Christian said, I joined the iTelescope community in 2015. So yeah, it's almost 80 years now. Yeah, it's going to be 10 years in 2 years. So I can wait to celebrate my first decade with iTelescope.
And it's fantastic because you're going to take us on a very special journey. So what's wonderful really about Andrealuna, she is an experimentalist. So she's a hand-on astronomer who actually knows what telescopes are like. Many don't, because they do all theory, which is also great, of course. So she's actually doing her talk in two parts, which is even more exciting. Today, it's going to be just a relax journey through the universe, the black holes and whatever. And next time, she's going to talk much more about her PhD. I hope I got that right. Is that right, what you're doing there?
Yeah, correct. So today we're going to have the first of two talks. Today is going to be more an introduction. So we're gonna start from our planet, and we're gonna get through all the universe, starting from our planet, going through the galaxy, into the star formation, and until we reach supermassive black holes. And in the next talk, I will talk more about supermassive black holes and their environment they have around them, and my PhD thesis.
Wonderful. So the stage is all yours. We're excited. I'm going to be quiet now. So please go ahead.
Thank you. Okay, I'm going to share my screen. All right. So I hope everyone sees my screen, my
yes, it's
presentation.
All good. It's good.
Okay. So please, everyone, feel free to stop me at any point. There are no stupid questions. And one thing that I like to say every time. So first of all, I love talking about astronomy and astrophysics. But one thing that I like to tell people is that math is just one of the multiple language we have to explain astronomy and astrophysics. And I mean, this is just one, but I like to explain this subject with words. So, and there are different ways to explain the same thing. So please, if there is anything that it's not clear, for many reasons, also I'm not a native speaker, so if I say something wrong, I'm sorry for that, but please stop me and ask me anything, because I want everyone to feel comfortable with the topics we're gonna talk about today. So I want to start my presentation with this picture. So, okay, didn't move, sorry. Okay, here. This is the Hale-Bopp comet that was visible in 1997. And although I seem very young, I was born that time, and I was 4 years old. And this is the first astronomical memory I have. Back then, I remember my parents showing me this comet, and I don't know if that was the kick that I don't know if that was what started my passion to this science or what, but I remember that since I was in elementary school and everything, astronomy has always been my whole, my only passion. If you asked me in elementary school what I wanted to be when I grew up, my answer has always been I want to be an astronomer. So I don't know if it was thanks to this comet or what, or if because I had the word moon in my name, but yeah, I was really meant to become an astrophysicist. So let's go ahead and let's start with this. This is a picture of our planet taken by the Imaveri 8 satellite. Is a Japanese satellite on a geostationary orbit, and this satellite has the objective of observing Japan every day. And as you can see, it's centered on Japan, and here we can see the red Australia on the lower part. So you can see here this bright spot. So first of all, yeah, the Earth is round. That's one thing we can see here. And you see this bright spot here. This is the reflection of the sun on the ocean, on the Pacific Ocean. And I don't know, when I first noticed that, I found that very amazing. How, like, it's actually a big reflection. If you consider the size of the circle, I mean, it's almost like 1/4 of the size of Australia, and the sun is pretty far away from us, right? I don't know. I wanted to start with this picture of the Earth because this is our house, right? This is the only planet we know where the life is on. But another thing that I liked about this picture is that if you look at this picture, you don't see any trace of life. I mean, if you look at our planet from the space, we don't see any trace of living form. I mean, if I was an alien looking at this planet, I would just be, wow, there are like red and green rocks there. I mean, I cannot tell there is actually something living on this planet. And it's something that made me think a lot in the past. So I just wanted to leave it here for you people to think about this as well. So we know that the planet, our planet, has an inclination, like rotates around its own axis, and this axis has an inclination of 23 degrees and 27 minutes. And so thanks to these inclination, we have season during the year. If we didn't have this sort of inclination, we would never, like, all the planet would experiment the same season over all year. And in here, I highlighted some of the most important planes that we have in our most important planes, like the equator and the Antarctic and the Arctic circles. And it's nice to see, so these are the same images taken by Himawari 8 in 4 different familiar dates, as you can see here, the 2 equinox and the 2 solstice. And you can actually see how, like, during the equinox and the solstice, like half of the planet, like exactly half of the planet is illuminated. I mean, at least, like, before I actually, so I mean, I made this collage, but before I actually took this picture, I didn't take, but I put together this picture. I've never seen, like, in books, a real collage, a real picture of the Earth. I've only seen, like, drawing of this, but this is actually real. This is actually what's going on in our planet. But what actually makes this everything possible is our star, the sun. So the sun is this big, relatively big bubble of gas that it's 300 million, 150 million kilometers away from the Earth. That means that the light takes 8 minutes to travel from the sun to the Earth. That means that the classic thing is, if the sun would explode, then it would take 8 minutes for us to see the explosion. But yeah, this is not a possible thing because the sun would never explode because of this mass. But we'll get about this later. But let's suppose that we are a photon and we're traveling with the speed of light. It would take us 8 minutes to get there. That is quite a long travel. So these giant object that we have, and it's like providing us the light that we need to live, as a surface temperature of 5700 Kelvin, or 5026 Celsius. So the surface temperature, it's hot, but not too, like, it's relatively hot, right? Because the actual hot part is the center of the sun, of our star. That's the part that's actually creating the photons, and that's the part that where we have thermonuclear reaction, in where the temperature arises to 10 to the 6 Kelvin. Christian, if you want to go with the first poll here, I have a question for you guys here. So we know that every object in the universe rotates around something. So what's the velocity that the sun revolves around the center of the Milky Way, if we can measure that velocity?
Yeah, we'll give him about half more minute so everybody gets a chance to think, because it's not something you answer every day, you know. So. Yes, Taz says he was going to ask for the frame of reference, but it's okay. Okay, let's see. I'm going to stop now and I'll share it. 1 second. There you go. So what do you think, Andrealuna?
All right. So actually, some of you, I guess, like the majority of you, overestimated the speed of the sun around the center of the galaxy. It's actually not around the center of the galaxy, but it's around all the mass that's within us and the center of the galaxy. And the actual speed that is called the local standard of rest, it's around 230 kilometers per second. That I mean, it's actually like quite kind of 200 kilometers every second. I mean, it's kind of like it's like the distance from Clemson to Atlanta every second, and it takes me 2 hours and a half with my car. So like I would like to travel at that speed with my car as well. So the actual distance, the actual speed is 230 kilometers per second. But good job, everyone. That was not an easy task, but if everyone is making any trivia, that could be a good question to ask to people. Not something that everyone, hears at the bar. But let's go back to our star. So this temperature produces a black hole, a black body radiation that peaks around that peaks in the part of the electromagnetic spectrum that we call visible light. We call it visible or optical because that's kind of an anthropocentric way of calling that part of the spectrum, because that's the part that our eyes develop to see. So we actually are able to see only that part of the spectrum that goes between 300 to 750. It's actually 380 to 710 nanometers, because that's the emission of our star. So our eyes can see only this frame of the electromagnetic spectrum, because that's where the emission of the sun peaks. Like, for example, if our sun was emitting more in infrared, our eyes would have been developed more to see infrared radiation and so on. So as you can see here, this is the peak of the blackbody radiation. Here we have infrared, and down here we have ultraviolet. This emission is very important. The fact that the peak spectrum of the sun lies in these waveband is very important for the life, how we know the life in the way we know it. Because if the peak was in the ultraviolet, for example, that wouldn't be very nice for the life, how we know, because we know that ultraviolet radiation can produce some modification of the DNA and can produce tumors. But that's just because our life, the life how we know, developed under this waveband. Again, we don't know how a different kind of life would develop with a different star that emits in a different waveband. And that's also another thing that we need to take into account every time we think, oh, are aliens out there? Okay, every time we go and search for another form of life, we have to think and we have to take into consideration that under different light situation, atmosphere situation, the kind of life that may have created on that specific planet could be absolutely different than the life that we know. But let's go back to the sun. These are some values. This is the mass of the sun in terms of kilograms. So here we have 30 zeros. This is the equivalent if we want to sum up. This is the amount of people that we need to make the sun in terms of mass. And this is the amount of planets Earth that we need to make the sun. So we're like, okay, calm down, like the sun is very big. And yes, it's very big because if we compare the sun to our solar system, the Earth is here. So yeah, it's quite big, and the moon is here. And you see Jupiter, like actually like all the center of mass of the solar system lies inside the sun, apart from the center of mass of Jupiter, of the Sun Jupiter system that lies just a bit outside of the center of the sun. Jupiter is the only planet that can move the center of mass of the Jupiter sun system. But then if we think that the sun is big, then let's take a look at other stars. And I don't know if you spot the sun here, but they heard this is the sun. So the sun is like a very tiny stars compared to other stars that we have in the universe. And that this is not even in the universe. These are stars we have in the Milky Way. Because this is another thing to take into account. Every time you go outside, even if you're in the darkest spot on the Earth, and then you're very lucky if you're there, all the stars you see in the sky are stars that lies within the Milky Way. Let's say that the farther object that your eyes can see is Andromeda Galaxy, but your eyes cannot see the actual stars there. You can barely see like this very light nebulosity where Andromeda is, but you cannot tell the single stars there. So all the stars that you see are within our galaxy, and these are some of the size. Even the northern star Polaris is quite bigger than the sun. But I mean, I found this amazing, right? Like we're just a tiny planet orbiting around a tiny star, and still, but this is actually what made the life possible, because we are the perfect condition. Our star is tiny, is stable, and doesn't have star winds that are too strong to destroy the life on our planet, and as a life that's long enough to allow the developing of the life. These other stars, the bigger they are, the more unstable they are, and so that wouldn't be very nice for life to grow in a nearby planet. But let's talk about where do stars come from. So I like this picture here that's from Goddard Space Center of NASA, in where you can see basically the whole cycle of stars depending on their mass. Basically, everything about stars life cycle depends on the mass they born with. Everything starts with the star-forming nebula. That's a nebula full of gas and dust, and from here you have these two cycles, and the length of these two cycles, as you can see here, this is longer and this is shorter because it's proportional to the length of the star life. This is for massive stars that are more than 8 to 10 solar masses, and this is for stars that are less than 8 solar masses. I like to compare this cycle, and I think it's also easier to comprehend for people that are not in this in the field, to humans' life cycle. So we can tell that basically the star-forming nebula is like when the star cycle of living for humans as well. So here, stars are like babies. It's a nursery here. This is where stars are created. And then we call them protostars. Before stars are, protostars are actually children, for if we want to compare them to humans. When stars start to emit visible light, then that's where they enter the main sequence. To be in practical, to use scientific terms, they enter the main sequence, but that actually means they enter their adult life. They start to emit visible light when in their core they start the thermonuclear reaction. That means they start to the hydrogen fusion, and this can happen by the PP chain, the proton-proton chain, for stars that are less than proton-proton, or CNO chain for stars that are less than 8 solar masses, or basically only within 10 to the CNO cycle for stars that are more than 8 solar masses. And then this life really depends, the length of the life, as I said before, really depends only on the mass of the star. The less the mass, the more the star is going to live and have a long life. So for stars that are less than 8 solar masses, they are called sun-like stars or dwarf. We actually have a long life, like for the sun. This long life is about 10 billion years, but we also have stars that are smaller than the sun that are going to live more than the age of the universe, so more than 13 billion years, until they reach the stage in where they burn out all the hydrogen and they start to burn helium, and so that phase is the red giant phase. And then depending on the mass of the star, like for example, once star like the sun won't have enough mass to burn carbon. So from the 3 alpha reaction, that is the thermonuclear reaction that burns, that fuses 3 atoms of 3 nuclei of helium in one of carbon, you get carbon indeed. And then the next step would be to burn carbon and so on. But the sun doesn't have enough mass to reach the temperature that's needed to fuse carbon. So the sun, so stars with the same mass as the sun will stop their thermonuclear life with carbon. And so after that, what will remain of the sun is this very dense nucleus made of carbon oxygen, and that's where the sun is going to end its life and become a planetary nebula. That are a bit more massive than the sun, so between 1 and 8 solar masses, we continue the fusion cycle until they reach this critical mass in where they cannot compress anymore, and they cannot reach like the temperature to go and fuse the next. They cannot do the next thermonuclear reaction that's needed to go ahead in the cycle. But anyway, the final step is for all the stars is to become planetary nebulas, and these nebulas are basically. In these nebulas, there is basically a white dwarf at the center that's releasing all the gases of the star, the outer layers of the star in the space. I will show you a picture of all these phases in the next slide, so it's going to be easier to understand like what these things look like in reality. But the important thing about this is that this is a phase in where you have interstellar medium enrichment. So basically, all the elements that got created inside the stars thanks to thermonuclear reaction, now they get released back to interstellar medium. And so here it's where you have the enrichment. So it's basically here, I like to think this as a reborn, where each star give back to the interstellar medium, and so a new star can born afterwards. When we have massive stars, so here you see the cycle can last billions of years, while for massive stars we have millions of years, so we have one order of magnitude less. We have stars that are more massive, so their life lasts much less. They become super red giant, and the same is happening here. So basically, this phase happens when they start to burn helium in their core, and soon after that, they start to do all this thermonuclear reaction until they arrive to have a core that's made of iron. When this happens, it's where the supernova explosion happens. So basically, that happens because iron cannot. The iron actually needs energy to be fused. It's not like I don't remember the right word, sorry. But anyway, when the thermonuclear reaction arrived like to produce iron in the core, then it's where you have supernova explosion. And this, depending on the mass of the initial star, can get to a neutron star or a black hole. And here as well, you have the release of all the outer layers of the star. So all these elements go back to the interstellar medium, go back to enrich the interstellar medium, and so a new cycle can start. And so this new star here will have in their medium all these new elements that got created by previous stars. That means that the first star that formed just after the Big Bang only had hydrogen, were only made of hydrogen, and just like just like very little percentage of helium. But then the second generation star that were made after this first generation star were made and exploded and everything, were enriched by the elements that were in the first generation, and so on. So the sun, for example, is a third generation star that has been enriched by the elements of this first two generation of stars after the Big Bang. So in here, I would like to show you some picture that I took using iTelescope in the past years. This is Orion, and just to show you how magnificent are the telescope in iTelescope network. So this is first of all a star-forming region, and to take this picture, okay, I only used 5 minutes of exposure. This is also like, so it's not, I swear, I'm not trying to convince you that iTelescope is a great, like has great telescope, but this is actually what it is, in the sense that Chris didn't pay me to do this, but I just want to say, like, 5 minutes of exposure and I got this image. Okay, so the reality is also that it's basically more than 10 years. I mean, I've been a student my whole life, and you know, the student do not get paid that much. So one thing that I needed to learn was how to make great picture with really low exposure time, because I didn't have enough points to take like very long exposures. And so I learned to extract all the signal that was in those damn pixel, even like with very low exposure time. But also that was possible only because, you know, those cameras have great CCDs and great telescopes. But okay, so this is a star forming region for a few reasons. So in here we find everything that's needed. We have a gas reservoir here, these dark nebulas. When you take a picture and you see dark nebulas, that's where it tells you we have stars here that are growing, but they are not born yet. Inside these dark nebulas here, we have nurseries of stars of protostars. When stars born, like we have inside the actual Orion Nebula here, then they start to emit visible light, as I was telling you before. And visible light, I don't know if you remember the spectrum of the blackbody spectrum of the sun, emits part of UV light as well. UV light is ionizing, is a ionizing light, and so it ionizes the gas, and so we actually see what's going on inside. So basically, here we have molecular hydrogen, and here we have ionized hydrogen. That's why we can see through this and not through this upper part here. We also have in this right part of the screen a reflection nebula. So basically in this image, we have everything we need. We have a dark nebula, a reflection nebula, and an emission nebula. In here, the dust is reflecting the light from the newborn star. Here, the stars are not born yet, but they are inside. And in this part, the newborn star are ionizing the gas, the hydrogen, that emits then in what we call H alpha. That's one of the emission line of the hydrogen. Another example of star-forming region is M16. So these are two pictures I took from the Hubble Legacy Archive. So everyone can go and download the raw pictures from the Hubble Legacy Archive and elaborate them as they wish. And this is another great example of star-forming region, but seen with two different wavelengths. This is the classic Hubble palette. So like this is big, but it's optical. So here we have H alpha, S2, and oxygen. And we see that we are dark nebulas here. So we don't know what's going on inside. And as I was telling you, dark nebulas are nursery of protostars. Indeed, when we go and see in infrared, we see a total different scenario in where we actually can see the stars, the protostars inside, that are not emitting in optical light yet, but they are emitting in infrared. And that's, I think this image is crazy. This is another image that I took with iTelescope. And here we have another star-forming region. You see here we have the dark nebula, and here we have an emission nebula created by these new star borning that are just born. This is another star-forming region, a row of Milky, always taken with iTelescope. We have the same thing we saw before with in Orion. We have the emission nebula, we have dark nebulas and reflection nebula. When we have these three elements, we know we are looking to a star forming region. If we had infrared vision, then we would able to see here that's actually I actually like to call these the alien nebula, because these shape reminds me of Alien from the movie, the xenoform from the movie. So if we had an infrared telescope, we would actually able to see all the protostars inside this dark nebula. And then we have this NGC 2541 that is also called the Red Horsehead Nebula, and where we have different elements. Okay, here we have some dark nebulosity here. We have these globular cluster that's not part of the complex. This is just like, this is actually behind. This is just here for perspective, but it's actually behind. And then we have this open cluster here of blue stars that are just born. So these stars are all part of the same complex. And this is the nebula that the emission nebula you see here comes, it comes from the gas that got ionized by these blue stars. And then we have this beautiful red star. So basically, stars, when they born, they have different color, and the color just depends on the temperature they have. And stars can also be, I like this picture, they can color, because you can actually see the stars have different colors. So you can also have an orange and a yellow giant. It only depends on on their mass and on their temperature. I was talking about open and globular clusters, and here we have two main different, like we have to picture the always with iTelescope. These are the southern Pleiades, also they're called like that. Is a beautiful open cluster, and there are two main differences about these two clusters, a part of their name. So first of all, open clusters have many less stars, as you can see, than globular clusters. But there is another thing that pops up: the color of the stars. Here, open cluster are newborn cluster of stars, and you see the stars are they're kind of together, but they're also like not so close together, because they have since they are collisional, clusters. So basically, each star is gonna go by its own, so they are not gravitationally bound. And they're young star. Blue stars means young stars. This is because blue stars are the more massive, the hottest, the most massive, and they are the one they're gonna die sooner. And so if you're able to see them, that means that structure is very young. And as a confirmation, we see here the black nebulosity that tells us this is a star forming region. Globular clusters instead are collisionless structure. That means they are gravitationally bound, and the stars are together there, and you see here the majority of the stars inside a globular cluster are yellow and orange. That means these are old stars. We don't see any blue stars inside the globular clusters, because those young stars have already died. These objects, globular cluster, have an average age of 13 billions of years, while open cluster usually have millions of years. So again, we have order of magnitude of difference. But then what happens when stars die? I told you that we have one option is here. We have planetary nebulas. And here you see the 4 different example of those, because one thing is like, you will never find 2 planetary nebulas that are like similar to each other, because each star will die in its own way. Among these four, this one in the lower left, I took this with iTelescope, and still, like, I don't know, every time I'm still amazed every time I look at it. And these three others are a picture that I took from the Hubble archive, and I reprocessed myself. I suggest everyone to try to do that, because if you want to prove your skills, these images, especially this one, the butterfly nebula, was kind of a pain to reprocess. But they are amazing. I think it's just crazy what the universe can make by its own, right? Like, they follow geometries. It's like, it's just incredible. And in here, one thing they all have in common is that, like, we see the hottest gas that's closer to the center, and the warm and the cooler gas that is from it's outside. And this is because these stars, so in each of these picture, the only star that's creating all this majestic structure is the star at the center. So if you, like, in this one, all these other stars are just behind us and the nebula, and the same thing is for other pictures. The only star that's responsible for all this structure is the white dwarf at the center of the nebula. While when we have massive star and they explode in supernova, this is what we get. So basically, we cannot, we have a supernova explosion, and this is the Vela. This is part of the Vela supernova explosion in the Vela constellation. I also took this with iTelescope. This was like actually 15 minutes of exposure with H alpha and oxygen 3 filters. And you see, like, it's just like, you see gas everywhere, because it was a really, like, a mess up. It was like real bad explosion. But the difference is that here you don't see a remnant. You don't know where the black hole or the neutron star here is. Here we can define where the white dwarf is, because the white dwarf is still a star that emits light. But in here, we have something that do not emit, at least not in optical. So the only way to localize neutron star or black holes are through the other different wavelengths. Like neutron star usually are localized through radio wave or X-rays. The same is for black holes, but only if they so if we have a pulsar, then neutron star, then we can localize them through radio waves, or if they have a companion, then they start to accrete matter, and then we can localize them with X-rays. Talking about black holes, we have three different kinds of black holes. The one I showed you before that can be created by star evolution are called stellar black holes, and they range with a mass that goes between 10 and 100 solar masses. Actually, these 100 solar masses black hole have not been found yet, in the sense that theoretically, like what I was telling you before, the first generation of star, so the first after Big Bang, could have generated black holes of this mass, but we don't know yet, but theoretically, yes. Then we have intermediate massive black hole that goes between the span, where their mass spans between 100 and thousands of black holes, but in this solar masses, sorry. But so this is this is also a picture I took with but in this case, for the intermediate massive black hole, is actually an open field. This is a big open question in astronomy, because we know they're there, because it's not possible that only like very small and very big black hole exist. There must exist also like intermediate massive black hole. but we don't know where they, I mean, and also we kind of guess where they are. We think they are inside globular clusters, but they're very difficult to locate and to to actually to locate. So these are still a big mystery of astronomy. And then we know that we have supermassive black holes here that are located at the center of galaxies. And the big question about supermassive black holes is like, how did they generate it? And this is still an open question in cosmology. But now Chris has a question for all of you. So where do you think it is the closest supermassive black hole with respect to the Earth?
Okay, this is so fascinating. So we'll give them a few more seconds. Yeah, maybe 20 seconds or so. And please don't, I see a lot of questions coming up, by the way. So please put them in the Q&A section. And once we have finished diving through the black holes and come towards the end, then Andrealuna will take some time to answer them. So give a few more seconds. Okay, let's share this. So what do you think?
Okay, now the majority of people got the right answer. Yes, Sagittarius, the closest supermassive black hole is Sagittarius A. That's at the center of the Milky Way. It's 8 kiloparsec away from us, so around 26,000 light years. It's correct. So again, to see, that means that everything that happens around Sagittarius A takes 26,000 years to get to the Earth. So everything we see about that black hole, like every picture that we see, like, oh, this is orbit of a star around a black hole, and we see the star disappearing and so on, that happened 26,000 years ago. Like, a long time ago, like during, that's crazy. The same is like, let's suppose there is a planet there and someone is looking at us from there. That means they are looking at Earth 26,000 years ago. So I don't like that. That's all the I'm putting like these hints like here and there, just like to make people think that finding life and be found by someone else, it's not that easy, right? Because like, let's suppose in this case, even if there is a planet with some sort of life that is located between us and the center of the galaxy, so this would be 13,000 light years. So 13,000 years ago, we didn't have any way of communicate like with radio waves or in any way with the with outer space. So we started, like, as human beings, we started to send communication outside of the Earth around 70 years ago. And so that means that the closest civilization that can actually hear us in some way has to be located within 70 light years. And so that's actually like reduces the chances to be found by anyone like a lot, right? So like everyone that says, oh, I think aliens are here, but like, how did they find us? Like, we didn't emit any, we were like in radio silence like for the majority of the history of the human beings and of this planet. So why did they choose this planet and not another one? As I said before, from outside, you don't see any, you don't have any proof of life. on this planet. And until 70 years ago, you didn't have any noise coming from this planet. So I don't know. These are always things that I like to leave there for people to think about. But let's come back to black holes. When talking about black holes, there are two important equations that we need to take into account. One is the Schwarzschild radius, and the other is escape velocity. So the Schwarzschild radius is telling us what is the radius of a mass to be basically telling us the radius of a sphere in where I need to enclose a certain mass for it to become a black hole. So anything could become a black hole, even me, you, or anything. The only thing is just like we need to enclose it in the right space. So for example, if we have an average human being of 70 kilograms, we need to enclose it in a space that has radius of 1 times 10 to the minus 25 meters. So it's gonna become very difficult considering like that would be smaller than the radius of an atom. But if we have the Earth, so something that has the size of the Earth, we need to actually put it like in something that has the size that's about 0.1 millimeter. And that's actually something more doable because some of our technology has already that size, right? And something with the amount, like something with the size of the Earth, like white dwarfs have this size actually, but they don't have this mass. That's why they're not black holes. The sun, for example, would need to be put in a sphere of 10 to like in 1 kilometer. In sphere of 1 kilometer to become a black hole, and this is like this is the size, this is the mass of the Milky Way, and this is like where we should enclose the Milky Way in to get a black hole. But when we do this, like let's suppose we do this, what would happen to the space-time that's around that object, right? So we know that thanks to like, I'm not gonna go too deep in general relativity here, but we know that when we have an object that's compressed into this Schwarzschild radius, so we have this object that's super dense, the space-time gets distorted, and the distortion is as higher or as more massive is the object. And here we have an example. For example, what is the distortion around the sun, the distortion around a white dwarf, neutron star, and so on. This is because these objects overall are denser and denser and denser. So just because the mass is compressed in a smaller and smaller amount of volume, sorry. And so what we have in a black hole is this is a quiet region in where like if you're a star and you're revolving around here, or a person or whatever, you don't even notice that there is a black hole. Like for example, the sun doesn't even know there is a black hole at the center of the galaxy, because like we are actually not rotating around the black hole, but we are rotating around all the mass that is within us and the center of the Milky Way. So if at this point you would remove the black hole at the center of the Milky Way, the sun would still rotate basically at the same velocity, because I mean the Sagittarius A is about 10 to the 8 solar masses, but the mass of all the star and matter that's between us and the Milky Way is much higher. So actually the black hole, the supermassive black hole, only affects a part of this mass. So basically the sun doesn't even, the sun or all the other stars, actually, they don't even notice that there is this potential there. Of course, the closest you get, and the closest, I mean, like you need to be very close to the supermassive black hole to start to feel there is this potential. We have the ergosphere, that's where you start to feel the potential of the supermassive black hole. And then you have the event horizon, where if you fall inside this, there is no, like, this is where it's like the no return point. Indeed, this is the second important equation I was telling you, that is the escape velocity, and this is the velocity that you need to escape the gravitational pull of an object. And everything has escape velocity, because as you can see here, this is the mass of the object, this is the distance you have, sorry, not the distance, but the size of the object, and g is just the gravitational constant. So I can put my mass here, and you would find an escape velocity that is like very, very small, so very easy to escape from a person. But you can see, like, for example, this is the escape velocity to escape from the moon. So if you want to launch a rocket off the moon, this is the velocity you need to provide that rocket. This is the velocity you need to provide a rocket to escape the Earth orbital gravitational pull, and so on. But if you want to escape the gravitational pull of a black hole, you need a velocity that's higher than the speed of light. And so not even a photon with the speed of light, that has a speed of light, can escape this gravitational pull. That means, like, if we have these four objects here trying to escape the gravitational pull of a black hole, maybe the Millennium Falcon would make it, just because we know that the Millennium Falcon can do hyperspace travels. But we don't know, right, what happens in galaxies far, far away. So basically what would happen, this is a question I always get, what would happen to a person when he approaches a supermassive black hole? This is a classic question I get. So what happened to a person if it gets close enough to a black hole? Well, you will get, this is a process that is called spaghettification. And it means, like, basically when you get, and it's due to the differential tidal force that the one part of your body gets with respect to the other side of your body. So your body would, of course, you're gonna rip apart because you're not elastic, but let's suppose you're elastic enough, you would get elongated and you would become like very, very long, because your feet or your head, depending on how you're, like, what's your position, will get a differential pull than the other part of your body, since like the gravitational potential there is so strong. Like, it's something that it actually happens on the Earth as well, right? Like, your feet gets a gravitational pull that is like a bit stronger than the gravitational pull that your head has, because like your head is like at the different distance from the center of mass of the Earth. But in this case, the gravity of the Earth is not that much. So first of all, human beings developed in this environment. So everything in our body is already calculated to take into account of this difference of forces. Secondly, the difference is, like, when you lay down, for example, that you're on the same plane, and so your feet and your head have the same gravitational pull from the Earth, like you don't even feel the difference, right? Because like it's negligible. But when you're close to a black hole, this difference is not negligible anymore, because your gravitational pull is so strong that actually you're going to rip apart. Or if you're made of rubber or like plastic or a very elastic material, you're going to become a spaghetti. Okay, you're going to just become very elongated. So here we have a picture on the right, and this is just an artist impression of what would happen when a star actually enters the event horizon of a black hole. So here we see the star, and here we don't see the star anymore. So we don't see anything just because the black hole doesn't emit anything. So actually, if black holes do not have any companion, so if they're not accreting mass from a companion star, there is no way to find them. We don't see them if they're alone, especially if they're stellar masses black hole. We don't have any way to locate them. In here in this representation, these like you see here, you're like, oh, okay, this is very similar to what we saw with the Event Horizon telescope. But these remember that Event Horizon was a radio telescope. I mean, it was an interferometer. It is an interferometer based like of different radio telescope, but with naked eye, optic visible light, you wouldn't see anything. And if a star just disrupts and gets sucked into the supermassive black holes, and doesn't create any accretion disk, then there is nothing that you can see. You can only see the star before and then the star after, so nothing. So that's the only way we can actually tell, oh, there's a black hole there. Even when you hear in the news that oh, there's been a black hole passing close to the solar system, how people know about that? Well, the only other way is like if you start to see weird gravitational movement of like the Oort clouds objects, or that's the only other way, like stars close to the Milky star close to the sun. If suddenly they start to have like a big perturbation of their orbits, then the only thing that can actually perturb them is a black hole passing by. So as I was saying before, we have a giant monster at the center of our Milky Way that right now is quiescent. This is Sagittarius A. So this picture I should have updated. Oh no, sorry, this is right. Oh, I should have updated with the actual picture of Sagittarius A. My bad. And these the two big bubbles you see here are called the Fermi bubble. And these are the remnant of a past activity of the supermassive black holes. Because not all the supermassive black holes at the center of galaxies are actually quiescent. Some of them, at least like, let's say that in the local universe, like close to us, the majority of them are not active. But when we go a bit backward in time, looking at galaxies that are a bit farther away, but like, for example, 30 is around 10, 15, 20 megaparsec from where we are, we start to see galaxy that supermassive black hole at the center that are active. Example, here we have the schematic representation of an what is called active galactic nuclei, in where you have a supermassive black hole, so a black hole that has a mass around 10 to the 6, above 10 to the 6 solar masses, and it's accreting matter. So that's where you have an active galactic nuclei, and these are the major, as I said, this is just a cartoon I made for my project, and these are the main component of the active galactic nuclei. And then we have here Centaurus A, that is the closest galaxy that shows these active this activity. And this is what we're gonna start. This is where I'm gonna end today, and that's where we're gonna start in next time. So next time I'm gonna talk about active galactic nuclei, and in particular, I'm gonna talk about the torus and its properties. So thank you for your attention, and I'm happy to take any question.